Just as a reminder for those of you who don't know this, this is the book I'm using, right? I'm literally using this book. This is not unlike the other lectures where I kind of did my own sort of pedagogical work. I'm not smart enough to create my own version of teaching this material. So I'm going straight through this. And what's interesting is that at this point, he takes a little bit of a diversion into what is an introduction or a hint into representation theory. And it actually is very interesting, and it's an important place to get that idea out. So this is a good way to do it. So what he does is he says, okay, we've got these transformations in this group. We're going to look at this in a different way. Right now we've kind of described everything algebraically. You know, we've got beta 1, alpha 1, beta 1, alpha 2 plus beta 2, and we've got this. This is all algebra. We're keeping track of the coordinates with this bookkeeping system, phi 1, phi 2. So, you know, in some sense we could have said, well, this is what gamma 1 is, and this is what gamma 2 is. And if we say gamma equals this, then, you know, gamma is the transformation beta after alpha. Right? So gamma equals beta after alpha. So keeping track of the real numbers this way is good, but we can actually be a little more efficient, possibly. Efficiency is always sort of in the eye of the beholder, but we could say this. We could say, look, say we had alpha 1, alpha 2. This is our transformation alpha, right? But let's write it this way. Let's write it as alpha 1, alpha 2, 0, 1. It's a little 2 by 2 matrix, right? And then let's take our coordinate vector x and we'll write it as a column vector x1 like that. And then if we were to do that, then f of alpha and x would be very efficiently written as alpha 1, alpha 2, 1, 0, acting on x1. And what does this give us? Well, it better give us a vector, right? Because we know that f takes a transformation and a coordinate, and it returns a new coordinate, right? So it better give us something that we can interpret as a new coordinate. We're now interpreting coordinates as 2 by 1 column vectors, where the lower number is always a 1 and the upper number is always a coordinate. So the result of this would definitely be alpha 1 x, right, plus alpha 2 and 1, right? So that clearly is the answer, right? So that's nice. We found a more annoying and complex way, actually. It's not even more efficient. But it kind of wraps things up in where we don't have to track around this stuff, phi 1, phi 2, gamma 1, gamma 2. We don't have to put superscripts on everything. So that's good. The price we pay, of course, is that we have to keep everything in terms of matrices. But this isn't good enough. That's just f. What about phi, right? So if I'm looking for phi beta after alpha, in this system I would write beta 1, beta 2, 0, 1, alpha 1, alpha 2, 0, 1. Could it be that the matrix product of this will give me the right answer? Well, what is the matrix product of this? And there I've written it out. And the matrix product, sure enough, it is beta 1, alpha 1, beta 1, alpha 2 plus beta 2, right? It is a perfect match with these two things, but that's not good enough. Does it come into a matrix that we've established is in a form of how we want to now describe our transformations? And it is. The scaling comes first, the shift comes second. And this is the correct new scaling, and this is the correct new shift. So this guy here is actually gamma, right? So we've now found a way to encapsulate this transformation, this abstract transformation on the vector space. We've turned it into hard and fast real functions, but now we've put it into a form of a matrix. So this is called a realization of the group, right? We have realized the group of transformations as a matrix, right? This is a matrix realization of this group. And furthermore, it would be called a two-dimensional representation of the group. So this is yet another place where we create the word dimension. We've now got a notion of dimension that has to do with not the dimension of the manifold, not the dimension of the vector space, not the dimension of the field that makes up the of which the vector space is constructed. And it's not the dimension of, I guess those are the three biggies, right? It's now yet another form of dimension, and it has to do with once we've created this thing and we want to write it down in some hard form like this, we might choose a matrix representation, and that matrix representation will have a dimension. In this case, it was a dimension of 2. The funny thing, though, is we could have chosen literally any dimension for this in this particular case. In this particular case, with this particular transformation, I'm not stuck with a 2 by 2 matrix. So to understand how we can do this arbitrarily, let's take a look at this interesting observation. If the coordinate x goes to x prime through this basic formula, right? That's the basic formula for f of alpha and x, right? Notice that I can take, this is a real number in the end, right? This is just some number. And I can square that number, and I can come up with another formula. I can come up with a formula for x squared in terms of alpha 1 and alpha 2. So the only complication here is notice alpha 2 squared. It's not alpha 2 to the 4th, right? Alpha 1 squared. So superscripts are serving two different purposes here. I'll try to remember to throw parentheses when I mean the exponent on the outside. But anyway, 2 alpha 1, alpha 2, x, right? So now you have a quadratic expression in x squared, and it's still a real number, and I can do this for a cubic expression as well, right? So with this, I could actually create another matrix that does all of the same work. If I wrote down this matrix, which is 4 by 4, and here instead I created the matrix x cubed, x squared, x, and 1, this matrix would also use this matrix to represent, I guess that's the right word, it's a representation. I'm going to use it to represent any given shift and scaling, right? So any given combination, well, any beta and alpha, right? Any given shift and scaling can be represented by this matrix, right? There's the scaling and there's the shift, and the scaling and the shift, that's the only two numbers in there. And I just create my space vector as all of the simple polynomial terms of x. Well, monomial term, right? X cubed, x squared, x, and 1. And then operating on, executing this matrix multiplication on this vector will produce another vector, which will also have this form, which will turn out to be perfectly the cubes of all of the, the first row will end up being the cube of the transformation. The second row will end up being the square of the transformation, and the third row will end up being just the linear form of the transformation. So each one will recreate the transformation, the actual value of the new coordinate, the square of the new coordinate, the cube of the new coordinate. And yes, if you multiply these two matrices together for an alpha and a beta, you will get the transformation for a gamma, and of course it'll become increasingly complex. So here you have a 4 by 4 representation of this whole operation on this space in here. Now, this is a very profound idea, right? It doesn't seem that important, and in fact, it seems insane, right? It seems like, why on earth would you do this when you could just, maybe this part here is good. Maybe I'll buy into the 2 by 2, but heck, that's even look at this. This is kind of you're sort of dragging this crap around, right? That seems like a waste. Why don't we just stick with, the basics here, the way we derived it? And you could, right? You could. But it turns out in physics, it's a relatively profound point that you're able to do this. And, and it can be done. Different particles of fundamental particle physics are attached to different representations of the same collection of symmetry transformations. Ultimately, that's where we're headed with all of this. It's a little more subtle because we have what's in those cases. It's the isometry group is a little bit more interesting than this, but we'll get there. It's a long way off, but we'll get there. Okay, so let's move on to the next subject for today. Okay, so back to this. Now, we have our two group elements, and we are now going to introduce another element to the transformation. It's not going to end up being another parameter, however. It's going to be a bit of a discrete operation where we flip the unit vector's direction, right? So the unit vector will go from facing that way. Oops, I better do a different color. Back to black, to facing the other direction. And under this transformation, under this flip transformation, x goes to just minus x, right? It's that simple. It's that simple. So when we allow for that, we're effectively allowing now, we're basically saying alpha 1 does not equal 0, right? But now it can be negative. Before we had alpha 1 greater than 0. But now we're allowing just to not equal 0. So now the manifold structure, right, in R2 is alpha 1, alpha 2, and everything is in except this line. This line is out, right? This alpha 1 can still never be 0. But now everything over here is okay, and everything over here is okay. One important thing to realize is that there is a special point here, right? The special point 1, 0. Now this literally does mean coordinates, right? This now means two things. It means the coordinates in R2, right, in the manifold. So it's the coordinates of the group point, but it also is the parameters of the transformation, right? So it's very convenient that way. And it usually turns out something like that. If you did Euler angles, you would plot in R3 3 angles, and they would be key rotations, right? So this makes perfect sense. But what's important here is that we still have a manifold even though we're missing this line, because we can take the actual group, right? So here's the abstract group X, and every point in X can be mapped into a region of R squared. It does not have to be that X has to literally map into R squared in its entirety in order for this to be a manifold. In fact, manifolds are defined exactly so that's not the case. That doesn't have to happen. It's just every region in X has to map into a region of R2. And there's rules about the overlap regions and things like that. So you could never find a region in X that maps to this, right? That would never be, because these points simply don't exist in X, right? There's no corresponding points. But this region might map over here, right? And so we still have a completely beautiful manifold structure. The point is, though, is that if we were to restrict ourselves just to parts of the group, just the parts of the group that are connected, we would have to limit ourselves to group elements that are entirely in this side of Rn, or entirely in this side. So what is connectivity? Well, if I have 2 points in the manifold and I can draw a curve between the 2 points, those 2 points are connected. So I can clearly draw a curve between these 2 points in the left side, and I can clearly draw curves between these 2 points here, this point and this point on the right side, and it's a continuous curve. Now, the whole idea of a continuous curve on a manifold is a very well-defined object. In our lectures on what is a manifold, we showed that if we have a parameter on a regular real line, call it lambda, I can create a function f of lambda into the manifold that produces all of the points along this curve, right? So I could tick out a parameter value lambda along this curve. That's all well-defined, and it's an important characteristic of manifolds that you can do that kind of thing for curves. The only way to define a curve, essentially, is to have a manifold, right? So it's really important. But I'm not going to go back to it. I'm not going to go back to that explanation, but I'll remind you to check into that if you don't remember everything about curves and manifolds. We're not using a lot of concepts on curves and manifolds, except this point about being connected. That's pretty important. So you'll notice that nothing on the left half plane is connected to anything on the right half plane. But what's important is, where's the identity located? The identity is located in the right half plane. So it turns out that if you have a continuous group that is disconnected, the connected portion that contains the identity is itself a group. So this is now a subgroup of the total group of all transformations, once we make the change that alpha 1 just can't equal 0, but it could be negative, right? Meaning allowing the vectors to flip, the unit vector to flip. So if we look at these, the connected component that contains the identity, this is a subgroup. This can never be a subgroup because the identity doesn't exist here. But it's not obvious that this would be a subgroup. For example, you could easily imagine a situation where I have this group element, right? And its inverse actually lies over here, right? And if that's the case, then this can't possibly be a group. The connected component can't be a group because the inverse of one of its members is over there. Turns out that does not happen. That does not happen. Now, in the rest of the chapter that Gilmore uses to discuss this, he talks quite a bit about the relationship between the subgroup of a continuous group that is connected and these disconnected parts. Now, in this example, we only have one disconnected parts. But we should keep in mind that there's no reason why you couldn't have two disconnected parts. One part that contains the identity and two other parts that don't. This was just all on a plane and it's disconnected in the plane. You can imagine disconnections in other kinds of ways that the point being, though, that only one of them will contain the identity. But whenever that happens, this will always be a subgroup of the total group. Now, I'm going to defer the discussion about the relationship between these sheets and this sheet, but it's very important to understand that there's two things important to understand. That if a continuous group is disconnected, the connected part that contains the identity is a group and the others are not, right? Because they don't have the identity. They can't be a group. But as far as being manifolds, this manifold structure of this connected part is identical to the manifold structure of every of the other disconnected parts. That's going to always be true for a continuous group. So this, as a manifold, is pretty much the same as this. They're both half planes, right? And that would be the truth for any circumstance, no matter how complex your continuous group is. In our particular case of the simple, this really ridiculously easy to understand continuous group, you end up with just these two half planes. Is pretty obvious. But you can imagine, and we will be talking about much more complicated versions of this. But I'm going to defer that discussion until a little bit later, when we're going to have to review some elementary group theory. We're going to have to review the idea of factor groups in particular, right? And normal subgroups, and things like that. This is elementary group theory, but it's the part of elementary group theory that you forget first. So I'll do a little lecture to review on those, but it's not time critical right now. What is critical is the last thing he says, or one of the last things he says in this chapter, which is the definition of a Lie group. He offers his definition of a Lie group. His definition of a Lie group, and we will compare it to others, is the connected portion of a continuous group. So in our case, the Lie group would just be this part, right? Not the whole thing, just this part. The connected portion of a continuous group with, an analytic group composition function phi. So the group composition phi of the connected portion of a continuous group must be analytic. And analytic we just have to understand in the most simple way, well, it's the definition. That means that this function on its domain of definition is always equal to its Taylor series expansion. That means you can Taylor expand this, and that is absolutely critical for this whole story. If you can't Taylor expand this, nothing works. And analytic basically means this function equals its Taylor expansion. Another way of saying you can Taylor expand this function. So that's it. That's the definition of a Lie group. Now, we're going to work with that to sort of tease it apart to make some sense out of it, and we're also going to compare it to some other definitions. But this is the one that Gilmore leans into, and his book's actually pretty hard. I mean, it gets into the basics of this stuff. So we now have a connected continuous group, a continuous group that is connected, and the group composition function, which is already known to be continuous, right? That's the definition of a continuous group, is this thing is continuous. And when we mean it's continuous in the coordinates of beta and the coordinates of alpha. So the actual continuous function looks like this, right? The muth component of the product of group elements beta and alpha, the muth coordinate, is a function of the eta coordinates of beta and the eta coordinates of alpha, right? And this is what's continuous, and this is what's analytic, right? We can do Taylor series in each of these variables. So it's worth explaining why this Taylor series thing is such a big deal. So let's lay down just an arbitrary Lie group. And the way I'm going to lay down an arbitrary Lie group is by just drawing a coordinate system, right? Because remember, now we're talking about a Lie group using our definition, and our definition is the connected portion of a continuous group. So we know from the fact that it's a continuous group that it is a manifold, and a manifold we can now think of it in terms of its coordinates. So we're thinking of everything in terms of our eta, and for the look and the work of things that we're doing here, we're going to call eta 2 just so I can draw it. So the first point I'll put down is the identity, which I'm going to put at the location 1, 0. Now, the coordinates of the identity do not have to be 1, 0. I can shift these coordinates around in all kinds of different ways. But 1, 0 we're going to use. However, that does not mean that we're back to using our very, very simplified group of translations and scalings, just because the identity was located at the same spot. It just so happens that for our demonstration, this is nice and easy to put the identity at 1, 0. Then I'm going to put some other group element out there called beta. And beta has its coordinates, right? So the coordinates of beta is beta 1 and beta 2. Now, because we're dealing with the connected component, because we are connected because it's a Lie group, so by definition it's connected, I can draw a line from I to beta. And I can draw that line any way I want, of course. It's an arbitrary process to draw that line, but I'm just going to pick one. And that's not saying anything important. It's a connected component. By definition, you can draw a line between any 2 points in the connected component of a continuous group. But each point in this plane, each point here represents a group element. So every point along this line represents a group element through its coordinates. So I could break this line up into small little pieces like this and mark off. When I'm marking off a spot along this line, I'm actually marking off a group element. So each of these tick marks now represents a different group element. Now I want to name all of these group elements. I want to name every group element that's ticked off along this line. So if I have, say, I got to pick a number now, capital M ticks, I'm going to call this first group element alpha 1, the second group element here alpha 2, and then this will be, say, alpha I, and then this last one I guess will be alpha capital M, right? And now the subscript is not to be confused with the coordinates. So alpha 1 has its coordinates as alpha 1 first coordinate, alpha 1 second coordinate, right? Now I'm kind of going into this two-dimensional feel, but understanding that this is just an abstraction of an eta-dimensional structure, it's then dot, 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 alpha 1 eta, right? There's going to be eta dimensions to this manifold, right? Again, you got to keep your dimensions straight. The dimensionality of the manifold is the dimensionality of the Lie group itself. It's the dimensionality of the connected component of a continuous group. So now notice, by the way, that it's the connected component of a continuous group. There's not necessarily a continuous group of transformations. So Gilmore's definition of a Lie group is very, very sparse. So now I've got these points along this arbitrary line chopped up into to a lot of different group elements. Each one is unique, right? Alpha 1, alpha 2. Now, there's nothing about this that says, oh, the group element alpha 1 times the group element alpha 2 has to equal anything, right? There's nothing about the relationship between alpha 1 and alpha 2 as group elements. In other words, alpha 1 times alpha 2 equals some other group element gamma, right? It doesn't necessarily equal alpha 3, right? These are just different group elements. What is true, however, because we're dealing with a continuous group, is that we can say that alpha 1 and alpha 2 are close together, because we can draw a neighborhood, an open set, that contains both of them. And that's sort of the definition of kind of being close, is if you're in the same open set. Or if I can create a neighborhood around alpha 1 that contains alpha 2. They're both in the same neighborhood. And that's how we create closeness, right? We're using the topology of Rn, mapping it back onto the group space. But now, when we talk about everything in terms of coordinates, we're literally using the topology of Rn as our open set. So alpha 1 and alpha 2 are in the same neighborhood. And what's also interesting is alpha 2 and alpha 3 are in the same neighborhood. And alpha 3 and alpha 4 are in the same neighborhood. And I can create all of these neighborhoods that link these adjacent alphas together. Now, let's look for alpha 1 inverse. Let's say alpha 1 inverse, let me erase some of this stuff. Let's say alpha 1 inverse. Alpha 1 inverse is definitely part of the group. It's part of the Lie group because the Lie group is a group, so the inverses have to exist. And it's also connected because the entire Lie group is connected. So let's put alpha 1 inverse right here. Let's say that that's the coordinates of alpha 1 inverse. So we know that alpha 1 times, well, let me just put them adjacent to each other for multiplication, is equal to the identity by definition. It's the continuity, the fact that this is a continuous group, that means that anything in this neighborhood of alpha 1 inverse multiplied by anything in the neighborhood of alpha 1 will ultimately give you something in the neighborhood of the identity, right? That's the whole point of being continuous, right? This function is the function that's continuous is the function a group element times a group element gives you a group element. This is continuous. It's another way. It's going back to the notion that phi alpha 1 inverse. This function is continuous on the coordinates of alpha. So literally, the continuous object here is phi mu of alpha 1 1 alpha 1 2 dot 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 alpha 1 eta semicolon alpha 1 inverse. See, now I'm having trouble with superscripts. 1 alpha 1 inverse 2 dot 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 alpha, whoops, where did that G come from? Alpha 1 inverse eta, right? This is the real function that is continuous, right? And so, but the continuity is basically telling me that something in the neighborhood of alpha 1 multiplied by something in the neighborhood of alpha 1 inverse will give me something in the neighborhood of I. But what's important about that is that I can now, and I'm going to draw this in red, I can take alpha 1 and alpha 2 to be in the same neighborhood, right? So what that means is that alpha 2 times alpha 1 inverse is going to be an element of some neighborhood of the identity, right? Because we just said that things in the neighborhood of alpha 1 times things in the neighborhood of alpha 1 inverse are in the neighborhood of the identity. So if alpha 2 is in the neighborhood of alpha 1, then alpha 2 times alpha 1 inverse is in the neighborhood of the identity. So that's actually pretty interesting, because what it's telling me is I can write a string of group elements. Let's do that. So this is the string that I'm talking about. We start with the identity on the far right, multiply by the inverse of the identity, multiply by alpha 1, multiply by the inverse of alpha 1, multiply by alpha 2, the inverse of alpha 2, alpha 3, the inverse of alpha 3, all the way to alpha m minus 1 to the inverse of alpha n minus 1, and then finally with alpha m, right? And of course, all of these are the identity. That's the identity, that's the identity, that's the identity, that's the identity. These are all the identity. So if you group them correctly, it's a sort of a trivial thing, right? This is meaningless. It's a bunch of identities multiplied by each other, and actually the final result is just what's left over, which is alpha m. But of course we don't group them that way. We group them in a way that's interesting to us. And that grouping goes like this. Alpha 1 times this inverse identity, alpha 2, alpha 3, alpha 2 inverse. I guess this would be alpha 4, alpha 3 inverse. It's all the way to alpha m minus 1 inverse. And the point about all of this is every single one, this is the key thing, every single one of these products, right, alpha 2, alpha 1 inverse, alpha 3, alpha 2 inverse, they are always going to be in the vicinity of the identity. Every one of these products is going to be in the neighborhood of the identity. That is, this neighborhood here, I better do it in blue, this neighborhood here, this guy's in that neighborhood, 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 all the way to this last guy. So now we imagine taking this sequence that we've written of products of group elements. So remember, each of these is a group element, right? The product of any two group elements is a group element. Just so happens this group element is close to the identity. I guess if I blew up, if I took this little blue thing and I blew it up, what I would see is there's the line, there's the identity element. All of these points are in here, right? That's the whole point, right? All these points are in here. But now if I took this to an infinite limit, right, where I have just I just increase the number of points here, I'm always going to have to deal with sort of the end of this line, beta. And this last group element eventually becomes beta. The more points I have, the smaller this divisions become. This AM actually becomes beta. And what you end up writing is that beta will end up being sort of this last element hanging out at the end of this whole thing without a product in front of it. So I guess the way you think of it is, okay, beta times I, right? That clearly equals beta. So now what do? Well, we take beta and we just start jamming in all of these other things, right? We jam in I inverse alpha 1 inverse, alpha 2 inverse, alpha 3 inverse. And you do this forever, filling in this gap with everything that's just a bunch of i's, right? Because all of these are a bunch of i's. So ultimately, this product equals beta, right? In its limit. The point is that ergo, this whole thing equals beta is my point, right? So that means that beta itself can always be understood as the product of an infinite number of group elements that are all near the identity, right? So if I just wander away from the identity and I start multiplying things over and over and over again an infinite number of times in a long infinite sequence, I will produce any finite element in this group, in this case beta. And that's important because that's this old canard, well, I shouldn't say canard because that implies that it's not necessarily true, this old or off-stated fact that understanding a Lie group right around its identity allows you to know everything about the Lie group. And that comes back to this idea that any group element can always be understood as the product of elements that are close to the identity in exactly this fashion. And that all comes down to the continuity idea, right? Two things in the same neighborhood multiplied by things in the same another neighborhood will produce products that are in, well, let's see. The product of two elements that are in the neighborhood of any two specific factors will always produce an element in the neighborhood of the product of those two specific factors, right? That fact is what allows us to do this. So it's all about the continuity that allows this to happen. So how do we exploit this? Well, now we think of this in terms of our composition function, which is a real mathematical function. We're interested in the composition function along this particular line of alpha I plus 1 times alpha I inverse, right? And because we have continuity and because we're dealing with a manifold, these things can be understood in terms of coordinates, right? And that's really important because that allows me to write this as well, what is alpha I plus 1? Well, alpha I plus 1 has the same coordinates as alpha I plus some small delta. I guess I'll call it delta alpha I. And then we have the coordinates of alpha I inverse, right? So my ability to write alpha I plus 1 is alpha I plus delta alpha I comes back to the fact that a Lie group is a continuous group that's a manifold. So now I'm talking about the coordinates of this. So this guy is, say, alpha I first coordinate plus delta alpha I first coordinate, right? This is a change in coordinates. And then the second coordinate is alpha I second coordinate plus delta alpha I second coordinate. Right, I guess I could put parentheses around this thing, right, to make sure it's clear. Although I did that before, and the parentheses were there to separate exponents, right? So you got to stay on top of things. So let me get rid of the parentheses. And you do this all the way to alpha I eta plus delta alpha I eta, right? So these are the coordinates, and this little piece represents a little bit of coordinate. And here we're not writing down the coordinates explicitly, but if you did, there's of course, not eta of mu. Well, there's mu of these, right? Well, there's eta of them, and we'll call each one mu. Let me go to red here. The muth coordinate of the product of alpha I plus 1, which is alpha I plus some little difference times alpha I inverse. And this is the product of two things. Well, this product, how about I say it this way? This product needs to be near the identity. So the way to write that down is you would say phi of alpha I plus delta alpha I inverse is kind of close to the coordinates 1, 0, right? That would mean well, I guess I should write it phi 1 is close to 1, and phi 2 of alpha I plus delta alpha I inverse is close to 0, right? And then that means that phi 1, phi 2, which is the product, is close to 1, 0. Right? That's, of course, leaning fully on this two-dimensional interpretation, right? Understanding this could very well be many, many, many dimensions. So this is the function that needs to have a Taylor series and needs to be equal to its own Taylor series. And we're going to lean on that quite a bit in our next lecture. I'm going to skip some of the material in the rest of this chapter. I'll probably come back to it when we have to do some more straight up group theory. But we're going to go straight into the properties of Lie groups, understanding this basic definition that a Lie group is the connected portion of a continuous group which is analytic. Now, we've definitely leaned on the connected portion when we talked about the line that connects any 2 points to the origin. And the fact of continuity showed us that any point in the group is actually a product of an infinite product of group elements that are all near the identity. And then we've kind of talked about how the group composition function can express this fact. The next lecture is going to lean a lot on the notion of the analyticity of it. We're going to start building things, taking these guys and making Taylor series out of them. Okay, see you next time.